Hello everybody and welcome back to another video. Today we'll be taking a look at another Project Euler question, and this will be anagramic squares, which is question number 98, I believe. Yeah. Okay, so I'll just let you have a quick read of the question. Feel free to pause it and think how you would solve this particular question. It's a very interesting question. Okay, now I assume you've read the question. Essentially, I'll just quickly summarize what the question is trying to say. We have a certain word, which we can, each letter can be assigned a numerical value. And we're interested in what permutations of the word would correspond to another English word. So in the example they gave, care would, if we shuffle the letters, it would become race. And now, here's the key thing. If we shuffle the corresponding digits, which each of the characters map to, then we get another square number. And we're interested in which pair of English words would have this property. And out of all such pairs, what's the largest square number which you could have? Okay, so this is a very interesting question. And as always, I'll just break it up into several main logical sections. The first logical section is, as you've noticed, there's essentially a words.txt file, which we're taking the words from. So we need to first get all the words from that txt file, and then store it in some sort of array, right? So that will be the first main step which we do. And then after we get all the words, we need to analyze which ones are anagrams. So the next section of the code will determine which are anagrams. And then we also need to do the same with numbers. So we essentially need to get a lot of square numbers and determine which square numbers are anagrams of each other. So after doing step 1 and 2, we would have identified care and race as being pairs, and 1296 and 9216 two pairs. But now here comes the tricky bit. We need to essentially map the list of anagramic squares with the list of anagramic words. And this isn't as easy as it might seem. You might be suggesting that, for example, with care, we could just try all possible 4-digit combinations, and for example, test C is 1, C is 2, C is 3, all the way till 9, and then do the same with A, R, and E. However, as you can imagine, this would be extremely inefficient, especially since we have to do this with several words. And this is a 16,000 character text file, so 2,000 words. So you can imagine how long this would take. That's clearly not the way. So instead, we have to do some sort of optimization. And the one optimization is we essentially map potential anagramic squares to anagramic words. And the reason why this is a significant improvement is, rather than testing all possible 4-digit numbers, which map to care, we only test 4-digit squares. So that would be at most like a couple 10, 20 numbers which we're testing, which is a huge improvement from testing well, like 1,000, 9,000 numbers, right? So that's the first improvement, but we can actually go a bit further. We can say that we can talk about the positions of care. So essentially, if we call this index 1, 2, 3, and 4, then the shuffling index would essentially be C would become 3, so then 1 would be in the 3rd position, R would be in the 1st position, and A and E would remain the same. So 3, 2, 1, 4 would be the shuffling arrangement, which is essentially what race maps to. And if we generate such shuffling arrangements for each anagramic word and each anagramic square, then we can identify which ones are similar. So care corresponds to race like this. 1296 and 9216 would also be 1234 and 3214. So using these two optimizations which I just discussed, we can essentially produce a list of equivalences between anagramic squares and anagramic words. And then finally, after we're done with these 3 steps, the 3rd step is the main bulk of the code. After we're done with all these, just check which one's largest. So check for largest square. And one further optimization which I haven't mentioned is these should be grouped by length, obviously. because a 5-digit square will never map to care, since it has one more digit than care has letters. Okay, so and now I hope that you've understood the main bulk of the actual code. Let's go and let's look how this is implemented in practice. So the first function g, which stands for generate, essentially just generates the anagramic squares and anagramic words. It's not too complicated here, unless you're not familiar with like file handling, for example. But assuming that you are, we essentially just open the file, and for each word, inside the file, if you open the file yourself, then you'll notice that it's essentially just one really, really long line. So what we do is we can split the line based on a comma, and then, excuse me, this will basically take every character within each word, apart from the first character and the last character. And this was the first and last are quotation marks. And okay, so these 3 lines will generate all the anagramic words. Sorry, these will take all the words, and now we need to generate the anagramic words. Now, here's where it gets a bit more interesting, in how exactly we're going to generate anagrams. So generating anagrams is a common algorithmic problem, and it's quite a neat problem in the sense that if we want to generate whether 2 sets of numbers are permutations of each other, what we can do is we can essentially sort the numbers, and if the sorted lists of both the numbers are identical, then the numbers must be permutations of each other. So what we do is we essentially group we group letters by their permutations of their word letters, and then for each of the word letters we append that word to it. And I'm just using a default dictionary here. If you're not familiar with that, feel free to watch a couple of videos on it. It's a very useful concept. And essentially, this line of code, these 5 lines, would generate all the anagramic words. And what we're doing here is, essentially the key of this dictionary is the sorted list of all the letters, and the value is a list of all the words. And what we're doing is we're just we're getting rid of all the values which are not greater than or equal to 2, because we only want anagramic squares where the number of anagrams is more than or equal to 2, obviously. If there's just one anagram, then that's not really an anagram by definition. And using pretty much the exact same logic here to generate the list of anagramic squares, now we can see that we have both the anagramic squares and anagramic words. So that's the function g taken care of. And now we have a couple of less important functions, and then we go to a more important function later. So this is effectively just flattening a 2D array. We'll use it a bit later on. There's nothing too complicated here. Essentially, we just convert a 2-dimensional array to a 1-dimensional array. It's not too bad. And now here we have group. Again, this is not too bad. Essentially, we have an array, and we want to output all possible pairs of elements inside that array. And as you can imagine, the reason why we're doing this is so in let's say this function, let's say that one particular word, let's say car, had 3 permutations. Let's say ACR, that's not a word, but it's okay. Oh, let's go with care. So care would have race as one. It would have carrot as one, obviously, and then maybe another one it would have is RAEC. I'm not sure that's a word, but let's just assume that it is. So we want all possible pairs of these 3 words, since all of them will be anagramic pairs. So then what we do is we have a certain array, and we essentially just generate all the pairs. So we have one pointer which iterates through every element inside the array, and the second pointer which iterates through the next element all the way till the end. After this, we generate all the pairs. Finally, we just return pairs. Nothing too complicated with these 2 functions. And this function is a bit more complicated. We essentially just sort by length for the anagrams. And if you recall, but back to our example on the whiteboard, we essentially said that the third optimization we make in step 3 is we group them by length, just so we reduce the number of redundant searches. So that's essentially what this function is doing. And the way we sort by length is we essentially have our anagrams. Now, I've made this general purpose, not anagramic squares or anagramic words, because they're both effectively the same thing, right? So, which if I pass a general function, anagrams, we don't know whether it's squares or words. And the first thing which we do is we flatten all the values, and then we generate all the pairs of those values. Okay? So now, after we've done this, we essentially just find their length, and then we append them to pair's length. And this pair's length is essentially just the length, it's essentially just the words grouped by their length. Okay, so that's sorted by length. And now the next thing we should do is we generate a map between words and numbers. So if you recall, back in step 3, sorry, one optimization which we made is we said that if we label 1, 2, 3, and 4 for C, A, R, and E, then the shuffling would be 3, 2, 1, and 4, right? So this is essentially the mapping which we're talking about, which is what this function is responsible for. And what we do is we create a map, map is a dictionary object, and we essentially just go through each letter inside the word, and we assign it a particular index value. Then we finally return the map. Okay, and now we have fun. I just couldn't think of a better name, to be honest. Essentially, we just check whether a number pair and a word pair, whether they're corresponding to each other. And if they're corresponding, if and only if, their maps align with each other, right? So we generate the maps for both these words, and if they're both equal, then we effectively return true as long as their lengths are equal. And this is very important because it could be that one of these lists uses one less number than the other, which is why it's important to check whether there aren't any duplicates within the words. And there will be duplicates if and only if the length of the set of values is less than the length of the values. Remember, the set data structure only has unique values. Feel free to look that up in case you're not familiar with that. Okay, so now we've gone through these 6 initial functions. Now, the remainder of the code is just grouping everything together. If you understood everything so far, the remainder shouldn't be a challenge. Essentially, we just put everything together. So we pull the square pairs, the word pairs, and then we just filter for the successful matches. And the successful matches will be if and only if this function returns true. So first of all, if the numbers are of the same length, and if the function returns true, then we append that to the successful matches pair. And finally, we need to determine which one is the highest square number. So we initialize an answer variable to 0, and answer is effectively the maximum of the 2 square numbers within any given match, right? And then we essentially just continue this for all possible matches, and finally we print our answer. So let's just see if this code works in practice. Okay, if we were to run the code, we can see that very quickly we get the answer of 1879. And 1879 is indeed our correct answer to question number 98. So that's pretty much it for this particular video. I really hope you enjoyed watching this video. Hopefully you learned something new about the way we've implemented this problem, and hopefully it's something you can implement in your own problems later on in life. So yeah, I thank you very much for watching this video, and I hope to see you in another video next time. Thanks for watching.